Have some questions on homework and such? You want to start with that? John Paul?
Projection.
A projection? What about them? Yeah. Do you have one in mind from the homework? Sure. Yeah, that's fine.
Yeah, because I'm really sorry. I was looking at old videos from last year and found it in the art. I was dedicated to it.
Okay. So here we go. So it says that a crate of negligible weight is being pulled up a ramp at an angle of 53 degrees with a force of 105 pounds. The ramp is 15 feet long and 8 feet tall. What is the amount of force being directed up the ramp? The key thing for me here is that we're given some specifications about the size of the ramp. So we can't assume this is like a unit vector projection. So to just kind of get a visual of what we're doing, you know, we have, you know, like some XY axis, you know, 15 over 8 up. Let's not make it that. Just do it like that. And then we have some other force at an angle of 53 degrees that's like 105 long. So maybe like that. And then we want the projection. So that's like that vector, right? So visually, that's what we're doing. Okay? And we want the length of that vector that we've drawn in orange. So we'll call that blue vector the pull vector with a P. And that orange vector is the projection of P onto R. All right. So let's start by writing our vector for the ramp. Yeah.
So the orange one is R.
The red is R. The orange is the projection of P onto R.
Okay, there's two different colors.
Yeah. Should I do it in a different color?
Oh yeah. Just don't hold on.
Here. I'll do this. We'll use what, like green or something, right? That'd be better. There. Yes. Well, the ramp isn't a force, right? Like yeah, if it's asking for like what amount of force is being applied up the ramp, we're like taking that force and we're finding how much of it is going in the same direction as the ramp. That's a projection. It'll always be that way. So we'll write our ramp vector. Since the ramp is 15 feet long and 8 feet high, we'll just call that vector 15, 8. Horizontal component, vertical component. Everybody's cool with that? The pull vector, we're told the magnitude for the pull vector is 105, because that's the amount of force that pull vector contains. And the angle for that pull vector is 53 degrees. So taking those two, I can then, what's that called? I can take that and turn it into a component form vector. Resolve, that was the word, the vocabulary word I was searching for. I can take that information, resolve it into a component form vector by just taking magnitude times cosine of direction, comma, magnitude times sine of direction. And then for my answer, what I'm really looking for is the magnitude of that projection of P onto R. So to do a vector projection, that's going to be the dot product of R and P divided by the magnitude of R squared times vector R, and then we'll do the magnitude of that. So I think I'm going to do this kind of all in my, at least the projection part all in my calculator. Probably just be simpler to do that way. Get out of there. So I'm going to start with the fraction. So R dot P is going to be 15. That's the x component of R, times 105 cosine 53. That's the x component for P, plus 8 times, that's the y component from R, 105 sine 53, that's the y component from P, divided by the magnitude of R squared, which would be like the square root of 15 squared plus 8 squared squared. So like the squared and the square root cancel each other out, and I'm just going to have like 15 squared over 8 squared. So 506 is like this number. Okay, so I'm going to have, now I'm going to do the scalar multiplication between that and R. So I have that number times 15, and then that number times 8. So 8402 and then 4481. Everybody's okay with what I did there? And now the, oh, yep, go ahead.
For what you put in your calculator, was it 15 times 105 and then what was the other?
Plus 8 times sine 105.53. That was the rest of the numerator. That's what you're asking?
8 times 105.
Sine 53. Yeah, just the dot product, right? So it's like the x coordinates multiplied together plus the y coordinates multiplied together. And then my last step is just to do the magnitude. So that's just square root of x squared plus y squared. So it'll get me down here, square root. And then my x is that 84 number, and my y is that 44 number. And about 9522. Should be my final answer.
What was the question for the force of
It wanted to know the force that was being directed up the ramp. So if you're pulling at a 53-degree angle at 105 pounds of force, only 95 pounds of that is actually going in the direction of the ramp. Which probably makes sense, right? If you think about if your angle was, the same as that angle for R, which would just be like tan inverse of 8 over 15. If you're pulling 105 pounds at 28 degrees, you'd expect all 105 pounds to be going up the ramp. Here you're 53 degrees, so like you're kind of pulling up as well as in the same direction as the ramp, so you're losing a little bit of that force. Mary?
What did you do to get 44.8 again?
That was just that 5.06 number I got from doing this coefficient, and it was just times the x component and then times the y component. That's how I got the 84 and the 44. Is that okay? You want to do another one?
Do 47.
Sure. It's a good contrast there, because what we'll do for 47, I think, will be a little bit different. Okay, here again we have a crate of negligible weight is being pulled up a ramp at an angle of elevation of 38 degrees with a force of 120 degrees. We're told the ramp has an angle of elevation of 25 degrees. What is the amount of force being directed up the ramp? So again, we'll draw ourselves a picture. Here's my ramp, where that's 25 degrees. And then I have some other force. I'll call that P. That's at 38 degrees. And we're looking for, again, that projection. So you're looking for like that vector. What do you notice is different about the information given in this problem versus the previous one? Right, so you're given no information about the dimensions of the ramp. What does that mean we can do? We can assume that it's 1. We'll just choose that for the length of the ramp. You could choose any length you want, but like, woof, why would you not choose 1? So if we do that and then we resolve this into a component form vector, we just get 1 times cosine 25, comma 1 times sine 25. And we do the same thing for the pull. The magnitude there is 120, and the angle was 38. So we resolve this the same way. Everybody,
Why can you just choose 1 for the ramp when they give you, even if they give you an angle of it? Like, why can't you just choose 1? But is it based on the length? That's much about the elevation.
well, here's the thing. It just wants us to know what amount of force is being directed up the ramp. So all I really need to do that is the direction of the ramp, right? The length of it doesn't really matter if we're just talking about how much force is being directed up it. I don't really care how long it is. So unless you've told me how long it is, I'm just going to not worry about it. I'm just going to make its length 1 and just worry about the direction on it. That question brings us, if we go back to this other one, the alternative would be you could have found the direction and then use the unit vector on this previous problem also. Like you could have done this and shortcutted through some of those nastier vector calculations. We'll come back to that and you'll see exactly the shortcut that I'm talking about. But you could do that in this previous problem also. Take that length and width and turn it into an angle measure and use a unit vector, or treat R like a unit vector. That would be okay. Okay. So again, then we want this projection, right? So now, because we're dealing with a unit vector, this projection calculation is much simpler. It's just the absolute value of the dot product of those two vectors, which is way nicer than what we had to do before. So let's go down and do that real quick. So I'm going to have cosine 25 times 120 cosine 38. Plus sine 25 times 120 sine 38. Done. 116.92.
Those lines seem to be absolute value now.
Yes, these are absolute values because this is a scalar as opposed to these lines being magnitude because this thing is a vector. Yep. Good notation question. Nolan?
And if it weren't a unit vector, you just have to divide by the magnitude squared and do scalar multiplication to r,
Mm-hmm.
and then take the magnitude of r.
Well, you then, yes. Yes. Or if you wanted to go back to this problem, you could do this and just make if you found the angle, you could make it a unit vector, and then you could do the dot product and get around doing that nastier projection calculation if you wanted to go that route. Now the angle is going to be kooky, right? It was like a big old decimal on it. But you could do it that way. It's okay. Does that, Elena, you kind of see what I'm saying there?
Yeah.
That was kind of your question, right? That I'm circling back to. Either way, it's okay.
So whenever you make one, it's always just going to be the dot product.
Mm-hmm. Yeah, whether it's given to you as like unlengthed, where you can just choose it to be 1, or where you're given a dimension and you could calculate the direction out of that and again turn it into a unit vector, which is okay. Right, that was a calculation we did in the notes previously, right? Where we wrote a unit vector in the same direction as blah, 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 blah. It boiled down to just finding the direction, like the angle, and then doing cosine angle, sine angle. Yeah, Ava. Sure.
I just don't understand how you know when it's 180 minus 360.
Sure. So the magnitude part you're cool with, right? It's just the direction.
Yeah.
So I'm going to skip doing the direction part. I'm not even going to worry about, or the magnitude part.
Yeah.
Okay.
Yeah,
That's fine? Okay. So I'm going to start by plotting my picture. So if I'm going to draw this vector, I'm going to go 3 over and then -4 down. Right? So this is my angle theta. And then just like last semester, this would be like my angle phi. The piece of the horizontal x-axis that's related, that forms part of my angle phi, is this end here, which is 360. So I notice that theta is going to be 360 minus, because we didn't go past 360, we haven't quite gotten there yet with my arrow, right? Phi, and we always calculate phi by doing the tangent inverse of the absolute value of the y component over the x component. So in this problem, it's just going to be 4/3. So I did the absolute value there. And that's all I'm going to type into my calculator. So I'm trying to do this the same exact way that we did last semester. So 306.86.
So if it's in like the first quadrant, it would just be
It'd be like 0, plus phi or whatever. So like, this is Ava's hypothetical, is you just have something here, right? So this is theta. So phi is literally equal to theta, right? And the part of the x-axis that has to do with that is 0. So theta is just literally like 0 plus phi.
okay, that makes sense. Thank
Is that okay? Again, trying to like make it the same, right?
Yeah.
When it's the same, it's like, okay, just the same. Yes. Yes. Or if you didn't learn it the first time, no.
Wait, so if it's in the first, the top two quadrants,
Whoa. Not, I mean, yeah, it's so you're always going to be using the angle having to do with the x-axis, right? So it's going to be 0, 180, 360, etc. So like if your angle was over here, your phi would be there. So 180, here your theta would be like 180, but you haven't gotten to 180 yet, so it'd be a minus. Is that what you're asking? If you're in the third quadrant, it would be 180 plus. If you've gone around more than once, it'd be like 360 plus. Yeah, it's just kind of, it's always one of those. Does that make sense?
Yeah.
So again, like I like the picture. I'm a visual guy. Becomes really obvious to me. Sure, I should be adding or subtracting just by looking at the picture. That's what I kind of default to. If you're not a visual person, that like you can memorize like, okay, in the second quadrant I subtract, in the third quadrant I add, and you can go around doing it like that if you want. Yucky, I'm not a memorizer. I mean, I have lots of stuff memorized, but it's like always in context. It's just not like rote memorization for the sake of memorization. And when I can just draw a picture that makes sense, whoa, it's okay. Anyways, I think you're done with me. I've said too much now. I'm over explaining. Who's next? John Paul.
Number 45.
45? Sure. You really like these vector problems, huh? Okay. What's the difference between this one and the previous question? Yeah, it's a reading thing. So if we're sledding downhill at an angle of incline of 15 degrees, so like there's my angle, so this is like 15 there. Okay with that? Alternate interior angle says that that's 15. So my theta is 345. Okay with that? It's for the ramp. And then it says Jenny and the sled weigh a total of 135 pounds. No pull is happening. What force is acting on somebody if you're just like gravity, right? If you're just standing still or just like existing, You have some mass to you. There's gravity acting onto you. Which way does gravity pull? Straight down. So that's my gravity vector. So what point is going to be at the end of that? 0, negative 135. So gravity vector is 0, comma, negative 135. And my ramp vector is going to be cosine 345, comma, sine 345. Again, we're not given any dimension for this ramp, so I'm just going to assume that it's a unit vector. So if I have all that stuff, I just want to project the gravity onto the ramp. And since that's a unit, or the ramp is a unit vector, I just get that. Or if I type it into my calculator, 0 times cosine 345 is 0. And so I have just like 0 plus negative 135 times sine 345, which is 34.9 pounds.
Mr. Cook, I know someone already asked you this, but I forgot.
It's okay.
How do you know, like, if gravity or the ramp goes on the bottom top? Because I know right here it doesn't matter because the unit vector is full. But unit vector here is 1.
The ramp is a unit vector.
Yes.
Yes.
So you don't have to go to the whole, you go to the shortcut.
Right.
Which is why you're using only that's the value of the two vectors times each other. But when you do the longer one, I know it matters like which one you're projecting onto the other.
Right.
So how do you know which letter the vectors on the bottom there? How do you know which one's like to the right?
So it says what amount of force is sliding down the hill. So this is like gravity is the force that we're projecting onto the hill. So you'd say the projection, and then the thing that's going onto is the subscript. Or I'm sorry, yeah, onto is the subscript, and the force that, or the vector you're projecting is like the argument.
So what's already there is going to be the subscript. Like the hill.
Yeah,
The new thing.
the thing that's not a force.
will be the subscript.
Yes,
And the thing that is a force will be
the argument.
the argument.
Yeah.
Got it.
Now read like 49 or 50. What's going on there? Let me grab one of those. When you read that, how many vectors do you hear? I read 3.
Create the ramp.
Yeah, so you have gravity, right, from the mass.
If there's mass, will it always be gravity?
Absolutely. And then we have a pull. So 48 degrees. And then we have some ramp. So the ramp I can resolve into a component form vector. And similarly, I can do the same thing for the pull. But I have three vectors going on. How do I? So it says what amount of force is being projected up the ramp. Those are both forces acting on the ramp, correct? So I'm going to project the force G plus P up the ramp, or onto the ramp. Well, I don't know. But here's the good news. This is actually not a problem. How do I do G plus P? Add the components, right? So, and then to do the dot product, what do? Just multiply the components and add them together. So it's going to be just 0 plus cosine, or 150 cosine 48. I'll put that in a parenthesis. And then times cosine 35. Oops, 35. And then a plus, and then negative 50 plus 150 sine 48. And then times sine 35. And 117.48. Well, I did, so here's what I did. So I did the x component of G plus the x component of P, and I multiplied that to the x component of R, right? And then I did the y component of G plus the y component of P. I multiplied that to the y component of R.
Wait, so is that G supposed to be an R up there?
So I have G, P, and R.
No, like in the orange, like to the right a little bit.
Oh, yeah. I'm sorry. Yes. This. Yes. Thank you. I would say a lot more sense. Yeah. Thank you. Was that good enough though, Ava, in terms of like? Yeah, the numbers just become like super tedious to write out. Like I'm just going to write that. Kind of just write that and like. Well, I mean, what would this point be down here? Right? Because which way does gravity pull? Down. Negative in the y. That's good? Okay. Sure. What time do we have to? I should have been looking. Class 3, 12:50, right? Nope, that can't be right. 1:30. Okay. All right, so I got like 15 minutes is what I want. That's good. I'm going to do section 8.5 in 15 minutes. What do you think? No, of course not.
Are we doing the forms at the end?
Yes.
In 15
Yeah.
minutes?
Yeah, this section is real straightforward. So we're going to talk about the three-dimensional coordinate system. X, Y, and the third component we call Z. So if I wanted to graph something in the three-dimensional coordinate system, I need an x-axis, a y-axis, and a z-axis. That's three-dimensional. How do I draw something three-dimensional on our sheet of paper that's two-dimensional? Well, we just have to use a little bit of imagination. So the way we draw that is like this, where you have to use a little bit of imagination. See the x-axis there? You have to imagine that like coming straight out of the board towards you. So like, you know, you're seeing it. Nolan.
So the x-axis, why doesn't the x and y-axis just stay the same and the z-axis?
Yeah, I don't have a good answer for you. That's the convention that we use, though, and everybody uses the same convention. If you don't use the same convention, it's just nobody's going to understand what you're doing. Which I agree. It's inconvenient.
I thought it's just confusing because usually the x is like left to right.
So what you're thinking about is like my x-axis is the sheet of paper,
Yeah.
and the z-axis is coming out from the sheet of paper, which is what we've drawn here.
Yeah, no, I get
Right?
that.
Like,
yeah.
I know. I understand. It's annoying. Yes, John Paul. Certainly. So typically, when we draw the XYZ axis like this, we only draw the positive end of it. So this is like the positive ends of this. These are like the negative little stubs here. We usually don't draw those in unless we need them because it gets pretty busy pretty quick. Everybody's okay with that? All right. Let's talk about how we plot a point in the three-dimensional coordinate system. And it's kind of like doing a vector projection, except there's no math involved, really. So we're going to start by just plotting something in 2 dimensions. So I'm going to just worry about plotting 3, 2. So along the x-axis, I'd have 3 tick marks. And along the y-axis, I have 2 tick marks. Everybody's okay there? And what I'm basically going to build here is a parallelogram. So 3 of the vertices for my parallelogram are going to be the origin, 0, 2, and then 3, 0. Everybody's okay with that? So I'm going to just kind of extend this out, extend that out, and that spot right there is like 3, 2. Everybody's okay with that? Now what I'm going to do is I'm going to lift what that parallelogram is like it's a plane, right? I'm now going to lift that entire plane 5 units in the z direction. So I'm going to start with the vertex at the origin because that's the piece that I have an axis for. So I'm going to lift that piece 5 units. And then this one that's directly parallel to it, I'm going to lift 5 units. And then I'm going to eyeball these pieces of lifting 5 units. Again, I'm just kind of estimating there. And then if I go ahead and I draw my new plane, it's like right there. Everybody agree? You see how we've just taken the same plane we had before and lifted it up? Basically drew a box, right? So that point there, that's 3, 2, that's been lifted 5 units in the z direction, is my point 3, 2, 5. That's how we draw, or how we plot something in 3 dimensions. Let's do it again. What do you guys say? It's a little bit weird, but it's one of those, like, you just have to practice it a couple of times to get the hang of it. So let's say we have the point 2, -3, 4, well, I noticed right away that my y has a negative on it, so I'm going to go ahead and extend the negative end of the y-axis so I can draw some tick marks there. So 1, 2, 3 tick marks on the y, negative y. I'll do like 1, 2 tick marks on the x. So I'll draw those 3 vertices. And then I'll draw my parallelogram. Everybody's okay with that? So that's the point 2, negative 3. Now I'm just going to lift all of these vertices 4 units in the z direction. So I'm going to start at the origin. I'm going to lift that point 4 units. I'm going to pick the point directly parallel to it, also on the y-axis, and lift that 4 units. And I'm just going to eyeball the other 2 and lift those 4 units. So this point here is the point 2, negative 3, 4. Is that okay? What if instead we had asked you to graph the vector 2, negative 3, 4? Nope. We just have to do one more thing. An arrow from the origin to the point. That's it. That's the only difference between plotting a point and drawing the vector. The vector just has that little arrow at the end. When I ask you guys to do this on the test, I would say, a half or to a third of students forget to draw the arrow at the end. They just plot the point and move on. Don't notice that it was a vector because of the wedge brackets. So just warning you now. But that's all that it's, that's the only difference. The last thing I want to talk about is just doing some basic calculation in 3 dimensions. So what I want to do is extend our definition of distance and midpoint to 3 dimensions. And it's actually a really easy conversion because all we do is we take the distance formula and add like a third component for it for the z component. So you have like the difference in x's squared, the difference in y squared, and then the difference in z squared, all square rooted. Same thing with the midpoint. It's the average of the x's, the average of the y's, and then the average of the z's. Whoa! I'm just like floored by that. Who's not surprised? Like that's as obvious as it could get, right? Like that's what we'd hope would happen. So just to do a numeric example to hammer this home, say we want the distance and midpoint for those 2 3-dimensional coordinates. So the distance is just going to be the difference in the x's squared plus the difference in the y's squared plus the difference in the z's squared, all square rooted. So what do we have? 14 squared plus 13 squared plus 13 squared, I think is 534. Sounds right. And then for the midpoint, just have the average of the x's and then the average of the y's and then the average of the z's. What's that come out to be? -1, -1.5, and then 4.5. Right, like, super easy. We're just plugging stuff into a formula. And the formula looks almost exactly like the two-dimensional formula, right? Just minor modification for the third dimension, but it's the same modification, it's the same pattern as the two-dimension. Really nice. At this point, you guys could now do 77 through 88. That was all of 8.5. I told you I could do it in 15 minutes. And we'll do the homework quiz next. Sound good?